All right, ladies and gentlemen, this recording has started. God help us. All right. The past. My pen decides it's going to work. Or not. Stand by. I said, do you need to call a penalty on me for a false start? Okay. In chapters 2, 3, and 4, we started with kinematics. Do we remember our description of kinematics, or what kinematics were? Sadly, no. That's part of it. That's part of it, too. More generally, yeah. So, there were 4 questions, right? The 4 questions were, where, right? What's happening right now? What's going to happen next? Oh, I should probably spell next properly. And then the last part, when. If we answer these 4 questions, we are describing motion. And that's what kinematics is about, describing motion. Okay? But there is one question that hasn't shown up yet. It's a pretty important question. What's the question? Why? And how is kind of the same thing, right? So, that last question, we haven't concerned ourselves with very much. We've kind of said, okay, it's gravity or something like that, but we haven't really got into the mechanism of why and how these things happen. In chapter 2, 3, and 4, we were just dealing with describing motion. Sometimes motion that was constant velocity, that was chapter 2. Sometimes motion that was accelerating, that was chapter 3. And then sometimes motion that was in 2 dimensions, and that's chapter 4. But now we want to start getting into the why and the how these things happen. Why is it traveling at a constant velocity? Why is it accelerating at 9.81 meters per second squared? Why is it slowing down? Why is it speeding up? We're going to start answering all of those questions in this chapter. And the short answer to that question is force. And that's what we get started in on chapter 4. Okay? Sorry, chapter 5. All right, so our discussion of chapter 5 starts here with this dashing lad right here. Look at his hair, isn't it? Like, you know, it's, wow, so much hair. So, all right, so this is Newton. This is the young Newton, as you can tell from his haircut. I mean, you know, so yeah, from what I understand, no, not ladies' man was not one of Newton's talents, from what I understand. But so anyway, Newton was born in 1642 on Christmas Day, so he's a Christmas baby. Okay, and a lot of the things that Newton did actually flowed out of work that Galileo had started years before. Now, it's not that long before, because Galileo passed away in 1642, and Newton was born in 1642, so some people feel that it was like, you know, well, Galileo died not on the same day that Newton was born, the same year though, but some people feel it was like a, you know, a cosmic passing of the torch. If you believe in that kind of thing, I don't know, whatever it is. So anyway, so Newton is English, lives on a farm, and you know, goes to school and gets to be about college age and heads off to school. But he's at college for a little while, and then he gets sent home. Not for disciplinary reasons, but because the plague had broken out in England. And so they said, hey, you know, large groups of people living in close proximity, really good for the transmission of disease. So they said, hey, why don't you go home, or else you're going to die. And Newton, being a smart person, went home. So, but anyway, so he's back on his farm. Farming's not really his gig. So he basically kind of sits around and watches everybody else farm, I suppose, walks around and thinks about stuff or whatever, And then allegedly, I don't know if it actually happened because I wasn't there, but, right? Well, that doesn't make the same sound as an apple falling from a tree. I mean, so that would make a squishy sound, like. That's true. And then allegedly, right? The apple. Wait. And then allegedly. Oh, this is gonna. Wow, this is not. What was in the top right? There we go. All right. And then allegedly, the apple falls from the tree. So, according to legend, Newton, watching the apple fall from the tree, comes to a realization that the apple falling from the tree is just the same same principle but different application as what makes the moon go around the Earth. Okay? Not that I'm aware of. No. So, okay. But Newton realizes, hey, and he puts the two and two together and goes, oh, it's the same thing. May or may not, along the way, have been having trouble making the equations work out properly. Okay? Go ahead, Mr. Basically, one of the things that Newton comes to the realization, in addition to the three laws of motion that we're going to study in Chapter 5, Newton also comes up with an expression to describe gravity. And he realizes that the force that causes the apple to fall from the tree to the ground is the same force that keeps the moon in its orbit around the Earth. And that leads him to kind of realize, oh, this, and this must be true. And that sort of, in addition to these three laws, Newton also, comes up with an expression for gravity that we'll do in Chapter 8. And for a long time, that was basically the only four things you needed to describe everything in the universe, basically. So, but was having a little bit of trouble kind of making the math work out properly, so may or may not have invented calculus along the way. There's some argument there about who actually invented calculus, but he was having some issues. He's like, this math doesn't work for me, I'll just invent new math. And when you're Newton, you can do those kind of things, Yeah, I mean, yeah, I mean, like I said, you could maybe try that like on a math test one day, be like, this wasn't working for me, so I just invented new math. I heard Newton did it, so I figure I could do it too. Problem is his works all the time, and yours would only work specifically for that problem. So you could try it though. And I said there is some argument about whether Newton actually invented calculus or by another guy named Leibniz, invented calculus, but
You say he invented calculus?
Yeah.
What equations was he using?
Well, basically the idea of the derivative and the integral to handle not discontinuous, but it's more like, yeah, but it's more along the lines of things are real easy to work out on straight lines, that math works really well when everything's a straight line, but when it's a curve, it's hard to do things with curves that you can do with straight lines, like take the slope and stuff like that. So he came up with a way where he could take the slope of a graph that isn't a straight line, or take the area under a curve that wasn't a straight line. That's easy to do on a straight line, not so easy on a curve, but he figured out a way to do it. So, and we call that today calculus, basically. All right, so he's at home, realizes these things, jots some stuff down, whatever. Plague ends, he goes back to school, becomes a professor, he's working, and about 20 years later, a couple of his friends come across work that he had done. Specifically, Halley's Comet, depending on how you say it, okay. Edmund Halley, apparently him and Newton were bros, and they were kind of like on one side of like the scientific community, and there was another guy named Robert Hooke. He was like the bad, evil scientist guy. Anyway, Halley kind of comes across these things that Newton was doing, and he's like, "Hey, what's going on here?" And Newton's like, "I don't know, just some things. I was, working out some math I was inventing, whatever." And Halley's like, "Well, this is pretty good. I think maybe you should publish this." And Newton's like, "I don't know. Seems like a lot of work writing a book and stuff, This is like an actual transcript of the conversation they had. I'm pretty sure. So that's what I read in the book anyway. So, but anyway, Newton publishes this book that he is pictured holding in this picture called the Principia, which is Latin for principles, blah, blah, blah. And basically it's his ideas about how the universe works. And we're here about 350 years later and still going strong, at least for the most part. Over time, we've realized that when we start getting to the extreme ends of the spectrum as far as conditions in the universe, specifically when matter starts traveling really, really fast, like towards the speed of light, Newton's ideas start breaking down a little bit. But I think we could probably forgive him. He didn't even really know what light was at that point in time. He was trying to figure it out, but he couldn't, and so that took a while, but whatever. So, but anyway, here we are 350 years later, and, still pretty much the same thing that he figured out back in the 1680s that, we use today to send guys to the moon or shoot off rockets to international space stations, sometimes successfully, sometimes not so successfully, but, but anyway, that's where we are. And a little bit later on in life, he becomes a politician, and that's when he earns his knighthood. So he is Sir Isaac Newton, not because he defined the principles that govern motion in the universe, but because, I don't know, he worked on some treaty between Britain and France, I don't know. Totally inconsequential. So, also, a little bit later on in life, had kind of a nervous breakdown. Apparently, one of the other kind of things that he was working on was alchemy. Are we familiar with alchemy? The science of trying to turn other things into gold. And at the time, it was a pretty legit venture. Like we didn't know about like protons and neutrons and stuff like that. So it was science. And but one of the things that alchemists would work with sometimes mercury, because it's cool. It's silver, but it's a metal and looks like Terminator 2 and stuff like that. But it does cause brain damage. So he had a little breakdown, but he got better. And anyway, so that's Newton, all right. And so, and that's Newton in a nutshell, right there. So I don't know if he's the smartest guy that ever lived, but top 5. I'd say probably top 5. Yeah. Yeah. Einstein's up there pretty. He's up there pretty high too. So. All right. Say again. We should develop a list. So. All right. So chapter 5, Newton's laws of motion. Remember that each chapter in your book has a big idea. And the big idea for chapter 5 is that all motion is governed by Newton's laws. Everything that we know of behaves in accordance with these ideas that Newton figured out, like I said, about 350 years ago. Now, like I said, when we get to extreme situations, right, some of it starts to break down a little bit, but it's still the same stuff that we use, like I said, even in things that as humans we consider to be pretty extreme, like space travel and stuff like that. These are the same principles that Newton came up with. So we start off in section 5.1 with Newton's laws of motion. And we start with Newton's first law, pretty inventive name for it, So we talked about the idea before that the answer to the questions why or how, the answer to that question is force. So let's define force. And we pull up this, our handy glossary, and it says that force is defined as a push or a pull. Thanks. That's extremely helpful in text glossary. So yes, a force is a push or a pull, that's true, but more importantly, as far as our working definition of force causes acceleration, okay? Force causes acceleration. Going back to chapter 3, our definition of force is what? Or sorry, our definition of acceleration is what? Do you remember our definition of acceleration? Come on. No definition of acceleration? Anybody? Change in velocity, right? And we said that, if we go back to our kinematics page, right, velocity is what's happening now, and acceleration is what's happening next, right? So force causes things to change. That's what forces do. And so Newton takes these ideas, one other thing, right underneath the definition of force on your page, you have this paragraph right here, okay? And it says, when you push or pull something, there are two quantities that characterize the force. The first is the strength, or the magnitude of your force. The second is the direction in which you are pushing or pulling. Because force has both magnitude and direction, it is a vector. So force is our next example of a vector quantity. It has magnitude, it has direction. But that also means that any of the things that we did in the last chapter, chapter 4, with forces, with displacements and velocities, right? Finding resultants, finding components, things like that, we can do all of that with force as well, because force is a vector too. Okay? Good there? All right. Newton's first law. Newton's first law says, two parts, okay? Says, objects don't start or stop moving on their own, and an object's motion does not change on its own. Those ideas are summarized in the two key points of Newton's first law. An object at rest remains at rest as long as no net force acts on it. An object moving with constant velocity continues to move with the same speed in the same direction as long as no net force acts on it. The Newton's first law has two key points. But when we look at them a little more closer, or a little more closely, I guess, right, we would see that they are very similar. So first, remains at rest is part of the first key point. And then the second key point says, continues to move with the same speed and in the same direction. Okay? Both of those are examples of what? Is there any change going on in either one of those? If something is remaining at rest, or if something is moving with the same speed in the same direction. No change in either one of those. What does that mean about the acceleration in both of those key points? There is no acceleration. Both of these situations describe zero acceleration. Okay? So Newton's first law deals with things staying the same. Newton's first law is things staying the same, which things will do unless they are, quote unquote, forced to do otherwise. This idea of things staying the same we refer to as inertia. Okay? Hopefully a term you've heard somewhere along the way before. Okay? So, by definition, pull this up here, and our definition of inertia, right? The tendency of an object to resist any changes in motion. Right? In case Simran's watching, right? We can go Espanol, right? Tendencia de un objeto, a resistir. How's my accent? Is it good? Yeah, I know. All right, so the tendency of an object to resist any changes in motion, meaning that if an object is at rest still, it wants to remain still. That's easy to convince anybody of. This box of colored pencils will not just start moving on its own because it's sitting right there, right? That'd be weird, okay? It doesn't happen. But the other part of it is harder to convince people of. If something is already moving, it wants to keep moving. Because the entirety of your experience, if something is moving, eventually what happens to it? It stops. So the prevailing thought at the time before Galileo and before Newton was, well, stopped must be the preferred state of motion. Stopped things don't start, and things that are already moving eventually stop. So there must be something special about being stopped. Newton said, no, that's not the case. Things will keep doing what they're currently doing unless they are made to do something different. Okay? Right, go ahead. Correct. There are certain types of forces. We'll talk a little bit more about that in section 5.2, where that force doesn't necessarily mean it's a push or a pull, but it doesn't necessarily have to involve contact. Okay? Are any of you familiar with the Voyager spacecraft, Voyager probe? Yeah, it's way out there. So, yeah, it's not of our universe. So, Voyager was launched back in the 70s, and its original mission was to explore Jupiter and Saturn. They went and took pictures and stuff like that. After that, they just let it go. And guess what it's still doing? Going. All right. About 5 years ago, maybe a little less, but about a couple years ago, Voyager effectively left our solar system because inertia. It was already moving. There's nothing to stop it. It just keeps going. Okay? It doesn't have an engine or anything like that. It just keeps rolling. There's no air resistance or friction, or it's far enough away from most gravitational forces that it just goes. It just keeps going. Right? Not really, because there's no air resistance. There's no friction. All those things that deteriorate machinery here on Earth don't really exist in space, but really, the chances of that happening are pretty remote because it's such a big place and there's so little matter out there that we kind of take our chances with that, Actually, we kind of take our chances with that pretty much every time we send a spaceship up into the atmosphere. That we basically kind of we can't really control all the stuff that's orbiting the Earth, so we kind of look at it and go, okay, hopefully nothing will hit this. Well, that would make things a lot easier now, wouldn't it? But anyway, Voyager, its mission is to just keep going until whenever, right? Until some other stuff, which we've kind of planned for that contingency as part of the Voyager spacecraft. We had a recording of Earth sounds. It's a gold record because record was the preferred recording video or audio recording device at the time. So it has bunches of hearts beating and babies crying and probably whistles too, I would imagine. So, but all those kind of things that we experience here on Earth, it's like a big record of these little couple second clips of this is what things on Earth look like. It's got information from world leaders at the time, hey, these are, we were the leaders of this planet at that time. I think Nixon was president, or maybe not Nixon. Anyway, so I think Nixon actually signed it, if I remember right. No, maybe Carter. Anyway, but we have president and couple other world leaders signed it. It has pictures of it has pictures of humans and DNA, but also can be. Well, see, that's kind of the other part is too, like, you know, we may come to regret this, but it also has a picture of like the Milky Way and like where we are in the Milky Way, so that, you know, if a hostile civilization finds it, it'll be easy to come invade us, you know. What? It's like just basically like attached to the side, like just kind of like they bolted it on and said, yeah. Well, the record is a record, you know, so an intelligent being. No. It has like a record of those recordings. So, right. Yeah, what's this? Like, why don't you guys use iPods? Like, you know, so like this is so inconvenient. Like, you can't take it with you at all. Like, but anyway, but it just keeps going because inertia, right? It's already moving. There's nothing to make it stop, so it just keeps moving. Another practical application of inertia. You know, you can try this at home, right? But I warned you, okay? And it's recording. I warned you, all right? So next Tuesday, right? You guys have a day off of school, okay? Although maybe, you know, your parents might have to work because it's just weird to have a day off on Tuesday. But maybe like on a weekend, you know, you roll downstairs. It's been a rough week, you know. Maybe it's like, you know, you had a couple tests on Friday or whatever, and so, you know, you get up late on Saturday morning, okay? You roll downstairs. I don't know, noon 30, whatever. So, whatever. It's been a rough week. So, but I mean, it's been a rough week, so you're kind of like, you know, yeah. So you come downstairs and your mom doesn't appreciate the fact that you needed extra sleep, and so she starts giving you a hard time, right? So be like, Mom, it's not my fault. Right? It's like, I learned in school that Newton said that objects at rest, you know, remain at rest. It's physically unnatural that I'm even down here talking to you right now. Like, you know, so she may hit you, I don't know, but you give it a try, see what happens. You'd be like, Mom, I'm learning something at school. So, but anyway, so Newton's first law deals with inertia, things staying the same. Things will continue doing what they are currently doing unless something makes them stop or makes them change. That thing that makes them change we refer to as net, I should probably show you this, okay? We refer to that as net force. Now, while I told you that force causes acceleration, when we really want to analyze what's going on, we can't just look at force, we have to look at what we call net force. So, the glossary tells us that net force is the sum of the individual forces acting on an object. Earlier, I told you that forces were vectors. The net force is the sum of forces, which means net force could go by a different name. What else could we call the net force? Might have to pull out a term from last chapter. It's the resultant force, which means we have to add forces together. If they're pointing in the same direction, easy, we just add the numbers. If they're pointing in opposite directions, we subtract the numbers. But if they're at right angles to one another, now we have to use Pythagorean theorem to find the resultant. So net force is just the resultant force, and that will become important as we start looking at applications of this stuff later on. Okay? Good there? All right. No homework tonight. I'll put it on for tomorrow night when we talk about our Newton's second law included in this discussion. So we'll get into that a little bit more tomorrow. Okay?